Hi friends, so today we will be starting in our second year intermediate physics, that is another interesting chapter, moving charges and magnetism. This is I think 7th chapter in our second year, moving charges and magnetism. Okay, this is our 7th chapter. From this we will get around 2 marks, 2 to 3 marks in MSET. In MSET you will be getting around 2 to 3 marks. Okay. So first of all, in moving charges and magnetism, you have to know about the subject first of all. What is moving charges? See, actually, in before years, that is until the enter of the scientist called as Oersted, the great scientist called as Oersted, what he has done is, while doing the experiment with a simple circuit, that is a battery, a bulb, tap key, etc., suddenly a magnetic needle kept beneath the circuit was deflected. So then he thought that why that magnetic needle was deflected. Then he went into the laboratory and he started researching. Then he found one thing, that means electricity at rest will have only electric charges. Electricity in motion will have electric and magnetic fields. So that is the main thing as invented from the deflection of the magnetic compass kept beneath the simple circuit. So this experiment, when he is teaching to the students, Mr. Oersted, ex-scientist, he found this thing. So until then we used to have electromagnetism, that means electricity and magnetism were different topics until then. After this, electricity and magnetism both are combined. Those both are called as electromagnetism. Okay. So from that only it has came this one. Enter the moving charges. Charges at rest have only electric charges. Charges, electricity at rest will have only electric charges. But when electricity is in moving, that means charges are in moving due to the drift velocity of the electrons, you have magnetic field vector also. Now he has given some directions. Okay, he has given some directions of the field. So in our syllabus we are having some important points which are not there in syllabus. I am not telling. Those are there in the syllabus only. We will be dealing today. Okay. So first of all we will be dealing about the Ampere's thumb rule, right hand thumb rule. First one we will be dealing Ampere's right hand thumb rule or grip rule. Okay. So this is given by the scientist Ampere. So what he is telling is, for example, if a conductor is carrying current PQ, carrying I, suppose if you are catching hold of with your right hand, okay, suppose if you are catching hold of right hand, Ampere's right hand, then what is saying is, thumb is indicating, please watch carefully, right hand grip rule. Thumb is indicating the direction of current flowing in the conductor and remaining curling fingers indicates the magnetic field around the current carrying conductor. You can see. So this will be in this fashion. Clear? So if you catch hold of a conductor carrying current with the thumb indicating the direction of the current, then remaining curling fingers indicates the magnetic field around the current carrying conductor. Okay, clear? So very easily you can find the direction of the magnetic field. Clear? If you watch carefully for this one, you can see, okay, the magnetic field is coming outside. See, in physics now, in future, for outside, I will be using as dot, outside, and inside I will be using this symbol, inside. Inside the board I will be using as this, outside I will be using as dot. So if you watch here, you can see outside, the field is outside. Here the field is coming outside, field vector. So when you catch, you can see field is coming outside. Okay. So here the field is coming outside. If you watch like this, if you put like this, you can see it is going inside here. So here in this direction it is going inside. There it is coming outside. You can see here, catching hold. Here it is going inside, field here. There it is coming outside. So like that you can explain the magnetic field direction. Okay, see here, it is inside. Magnetic field is inside. There it is outside. So like that you can explain the thumb rule, okay, statement. Okay, na? Clear? We will do one more experiment by using right hand thumb rule or grip rule. One more I will give you to find out. Okay. For example, see here. This is a conductor carrying current AB, carrying current I. Now we will be using the thumb rule and we will finding out the direction. Now can you tell me for this one, this side and this side. Suppose this is P end, this is Q end. So what will be the direction of? You can use the right hand grip rule or Ampere's right hand thumb rule. Now for example, if you see carefully, see here, current direction, put your thumb in the direction of current. You can see the magnetic field is going inside. The remaining curling fingers indicates the magnetic field. So here the magnetic field is inside. Here you can see the magnetic field is inside. Clear? And you watch this side. If you watch this side, here, see, coming outside, coming outside. So here it is outside. So these are the symbols. With this you can understand better manner. Okay? These are the symbols you can understand in a better manner, please. So here in this side you can see, okay, going inside magnetic field. And here if you observe, see, current direction, putting the thumb here, see, field is coming outside from the board. So you can indicate with this symbol. So like this you can understand and you can solve many problems in physics by using this thumb rule. Okay. So this side it is coming outside and this side is going into the board. So this is how you will be using Ampere's right hand grip rule, please. Okay, clear? Let us go to the next item now. Now next one is Biot-Savart's law. Second one, very very important. Biot, two scientists, Biot and Savart's law. Okay, so these two are individual scientists, please, not one scientist. Biot and Savart's are two different scientists, please. Okay, so they has given this law. They has given this law, please. Biot and Savart's, two different scientists. So what they have given is, for example, this is a conductor carrying current PQ. This is a conductor carrying current. Okay, it is carrying some current I in this direction. Now at the point P, how to calculate the magnetic field induction? How to calculate the magnetic field induction? B, dB. Okay, for a small elemental length, please. For a small elemental length dl. Okay, this is the direction. Okay, so dl is along the direction of current, please. So this point P is around at R and this is making an angle theta. Now what is Biot-Savart's law saying? To calculate the elemental, because these elemental lengths will be so many. In this entire wire, this elemental lengths will be so many. So due to this small elemental length dl, okay, at the point P, which is at distance R, okay, which is making an angle in this direction of the current. How to get B there? So for that he has given, those two scientists given expression, dB is equal to mu naught by 4 pi I dl sin theta by R square. But this is scalar form. Isn't it? Scalar form. That means dB is proportional to magnetic field induction is proportional to I and it is proportional to dl length, elemental length, and it is proportional to sine angle, and it is also proportional to inversely square of the distance. See how many relations you have found out? Directly proportional to current, elemental length, sine angle, and inversely proportional to square of the distance between the point where assumed from the elemental length. So combining all, you are getting this. This is constant k. We all know mu naught by 4 pi is equal to constant, and already we know mu naught value 4 pi into 10 power minus 7 Henry per meter. So this is scalar form. Suppose in the examination they may ask you in vector form. So what is vector form? What is vector form of Biot-Savart's law means? Same thing I can write in this fashion. See, for mu naught by 4 pi I will write k I. Now here what I will do is dl cross r by r cube is equal to dB. This is the formula. Here k is again mu naught by 4 pi please. So it is a vector form, dl cross r. Don't write r cross dl please. dl cross, dl is in this side. dl cross, okay, you can use the right hand curl rule also to find the direction. Okay, along the direction you can see that this will be the direction. For vector product already explained in first year, you can find the direction by using right hand curl rule. Okay, in which direction you are going, you can curl the fingers. Okay, dl cross r. This is dl cross r. So you can get, this will be the direction. Okay, na? So this is the vector form. K is mu naught by 4 pi I dl. So when you expand this one, what happened? Modulus of dl, modulus of r sin theta by r cube. R and r cube gets cancelled, r square is left over. So dl I dl sin theta by r square. So this is the vector form. In the examination they will be asking. This is scalar form of Biot-Savart's law. Okay, clear? Now let us go to further. After learning about Biot and Savart's law, or Biot-Savart's law, scalar and vector form, let us go still further. Okay? That is the next one. Let us try to understand the concept. That is, for example, a finite wire is given for you. For example, if a straight wire, see in MSET questions these are coming nowadays, straight wire and finite. It's a straight wire, finite please. Finite means there is limits, borders are there, top and bottom. Straight wire, finite. Okay? Straight wire, finite wire is given of length L. I am showing here. Finite means there is a fixed length here. Okay? Let P is a point. Okay? And it is a perpendicular distance, this one. And let this distance be D or A. See, some books they are following A, some books they are following R, some they are following D. Better you can follow D or R distance. This is perpendicular distance here. Okay? So in such a case, this is a finite wire, long wire of length L, and you can, and I is the current passing in this one. I is the current passing. In such a cases, how to get the at point P B value? So in such cases, what you will do is drop two lines from that end points. Drop two lines from the end points, and this is theta 1 angle, this is theta 2 angle. Okay, theta 1 is the angle for first one. Let's name some letters as P, A and B. Theta 1 and theta 2 the angles. Now to get B at this point, B at that point is given by, okay, I'll write it as mu naught by 4 pi I by D or A. I'll write D only better. D or A, then we'll follow I by D bracket sin theta 1 plus sin theta 2. This is the standard formula for this one. Okay? When finite wire is given, borders are there, top and bottom with length L. I is current carrying. At a point B, okay, the magnetic field is given by mu naught by 4 pi, of course it is a constant. Again, mu naught is equal to 4.10 power minus 7 Henry per meter. I is current flowing. D is the distance, perpendicular distance from this point. Okay, this is the distance D to the point P. D or A or R, anything you can assume. Sin theta 1 plus sin theta 2. This is the general form. For example, in the examination they may give this angle 30 degrees. This they may give 60 degrees. Put the values there, you will get it. Mu naught by 4 pi I by D, sin 30 half, sin 60 root 3 by 2. So like this you can put the value. If suppose if they give like that, then you can put the value as mu naught by 4 pi into I by D. LCM if you take 1 plus root 3. And what are the units for B? See, for units for B you can have so many. From F is equal to MB, F by M is equal to B, that is Newton per ampere meter, Weber per meter square, or simply Tesla. Nicholas Tesla, scientist name. So the SI unit of magnetic field induction B, magnetic field is given by what? Either Newton per ampere meter or Weber per meter square or simply Tesla. Any unit you can use. Okay. So like this you have to solve for finite wire. Now let us go to the next item. Next one. Okay. Now what we will do is, after learning about finite wire, let us go to, already you have solved one small problem. Now let us go to infinity wire. Infinity. See, in the examination, what will instead of infinity they may tell us long wire. Either infinity or long wire, both are same. Infinity wire. Okay? Infinity wire. Finite తీసేద్దాం. Next case ఏంటి? Infinity long wire. Infinity అయినా long అయినా ఒకటే. That means what happens? There is no border. Infinity. Here also infinity minus no border. Watch carefully the same figure. Here what happens? What was the formula before for finite? Field is equal to mu naught by 4 pi into I by D into sin theta 1 plus sin theta 2 for finite wire. This is the formula for finite wire. Mu naught by 4 pi into I by D అని రాయొచ్చు, లేదా I by A లేదా I by R. ఇది finite. ఇప్పుడు జాగ్రత్త అబ్జర్వ్ చేయండి. The wire is going to infinity, long wire. That means when you join this line here, where the lines will meet? Infinity lines ఎక్కడ మీట్ అవుతాయి? చూడండి, లైన్ ఉంది, ఇది మీరు డ్రా చేస్తున్నారు, బట్ ఇట్ ఈస్ గోయింగ్ టు ఇన్ఫినిటీ. సో వాట్ హ్యాపన్స్ ఫైనలీ? దిస్ యాంగిల్ బికమ్స్ 90. You can't join. Both becomes parallel. So what is the angle now? 90. In the same fashion, what is this angle? 90. మీకు అర్థమవుతున్న పాయింట్ ఇక్కడ. See, this is wire is going to infinity. If you try to join whatever, it is going infinity. You cannot join. So whatever your line joining, it becomes like this straight. Okay. So what happens? This angle becomes 90 degrees for long wave. So what happens here in this formula? Magnetic field is equal to mu naught by 4 pi I by D into sin 90 angle plus sin 90. So mu naught by 4 pi into I by D into sin 90 1 plus 1. That will be B value. Therefore, magnetic field induction or magnetic field at a point P due to current carrying long wire or infinity wire, therefore given by mu naught by 4 pi, which is constant, I by D, and this is 1 plus 1 into 2. Or simply you can write this one as, don't cancel this 2 times, keep it like that only. Mu naught by 4 pi 2 times I by D. So this is the final formula for magnetic field for infinity wire, long wire. Okay, I is current passing, D or A or R distance between the point P and this one, perpendicular distance, and mu naught by 4 pi is constant. 4 pi value మీకు అలాగా తెలుసు, it is 4, mu naught value tells 4 pi into 10 power minus 7 Henry per meter. Clear? So this is regarding infinity long wire. Okay. Now suppose it's the same thing. Question asks semi-finite, semi-infinity. Okay na? Same thing ఏమన్నా semi-infinity. అప్పుడు ఏమవుతుందో ఒకటి క్లోజ్ చేద్దాం. Semi-infinity చూడండి. Semi-infinity అంటే ఒకవైపు బార్డర్ ఉంది, ఇంకోవైపు బార్డర్ లేదు. దిస్ ఈజ్ సెమీ-ఇన్ఫినిట్. ఇన్ఫినిటీ అంటే లాంగ్ వైర్ అంటే అటు ఇటు బార్డర్స్ లేవు. దిస్ ఈజ్ వాట్ నెక్స్ట్ వన్ semi-infinity wire. That means here border is there, point P same as distance D or A or R, D or A or R, and this is going, this is border. So this ఏమవుతుంది అప్పుడు half of the initial value. ఇందాక లాంగ్ వైర్ ఇన్ఫినిటీ లాంగ్ వైర్కి ఏమొచ్చింది మనకి B, we got it as mu naught by 4 pi into I by D into 2 వచ్చింది. ఇదేంటి ఇన్ఫినిటీ వైర్కి ఫైనట్ ఇదేంటి సెమీ ఇన్ఫినిటీ సగం, సో by 2. Then what happens for semi-infinity wire, magnetic field induction at the point P is given by, where P is the distance between perpendicular distance, that is D or A or R, that is nothing but mu naught by 4 pi into simply I by D. Units ఏంటి చెప్పాను కదా, either Tesla or Webers per meter square or Newton per ampere meter. Any unit you can write down. I is the current, D is the distance between the point P and the wire, and remaining all the constants. ఇది దేనికి ఇది semi-infinity. Okay, very easily you can remember the formulas, and also you can use in the examination for numericals, please. Very easily you can score the marks in MSET or NEET. Okay, now after completing the semi-infinity, okay, we'll go to the next one now. Okay, we'll go to the next one, that is circular coil carrying current. చూసారా ఎలా ఉన్నాయి ఒకటి one by one I'm telling very clearly. Next one is circular coil or loop. Okay, circular coil or loop carrying current I. For example, this is a circular coil. Suppose say this is the direction of current, this is the center C, and let this radius be A or D, anything, and you can take R అయితే R, okay, or A or D, anything. ఎందుకంటే we are using the formula as generally D వాడుకుంటున్నాం మనం. D వాడితే take the radius as D. If you are taking A, put it as A. If you are using R, use as R. So this is a coil having only one turn, number of turns. Let the number of turns be one turn. For n turns, you can use the formula again extend. So in such a case, what happens? It's a circular coil. Now for such a case, at the center, చూడండి ఒకసారి, again your right hand curl rule use చేద్దాం, right hand curl rule చూడండి. So curl your fingers, 4 fingers like this, along the direction of the current. So the direction in which the thumb is showing, that will be the magnetic field direction. So magnetic field ఎక్కడ ఉంటుంది లోపలికి. In this case, if you observe carefully, the magnetic field is inside the board. See? Curl the finger along the direction of the current. Okay? So, in which you can see thumb is going inside. This is the magnetic field. So, in such a case, what is the magnetic field at the center? Magnetic field for the circular coil carrying current is given by simply mu naught by 2R into I. If one turn is there. If suppose you are having n turns, multiply with n. This is general formula. Mu naught Ni by 2R. Where R is the radius, you can use R or D or A. I current flowing, mu naught constant 4.10 per minus 7 Henry per meter. N number of turns. Suppose you can turns 1 only అనుకోండి 1 పెట్టేసేయండి. అప్పుడు జనరల్ ఫార్ములా ఎంత ఉంది సెంటర్లో? You will have B is equal to mu naught I by 2R. This is the general formula. Okay, if n turns are there, you can multiply with n. Clear? And this is for what? Circle center. Okay, magnetic field at the center of the circular coil carrying current. Clear? Next, suppose it's the same thing we are asking for semicircle. Same thing we are asking for semicircular coil. Okay na? Suppose ఇలా ఉంది. Same thing they are asking for semicircular, same thing again, Again field inside. If you use the right hand curl rule, magnetic field inside, this is the radius. Okay, radius R or A, anything. Now at the point C here, center, semicircle is the half of the circle. So in that circle, how much we got for circle? Mu naught I by 2R for 1 turn. This one divided by half. That's all. This is the value. Okay, Weber per meter square or Newton per ampere meter or Tesla. This is the value. Don't multiply this one. 4R, keep like that only. This is for what? Semicircle. Okay na? Clear? So semicircle ee vidhanga teesuko ela meer ennaina teesukochandi. There is no problem, anything andi. Next we will go for arc of a circle. Next I will draw here arc of a circle. Okay, here same thing, current carrying, arc of a circle. Let this angle be some alpha or whatever thing. Okay, let this angle be some alpha or theta or whatever thing. Total angle alpha. This is bisector. So again same thing, current carrying, you can see magnetic field inside. Anything you can take, magnetic field inside. Okay na? You can see. So magnetic field, in an arc unnappudu enti, arc of the circle is center kada, radius R. See, this is radius R, you can see. Okay. So in such cases what happens? Arc of a circle ki formula emavutundandi, magnetic field. Okay, at this point C, B is given by mu naught I by 2R as it is. Circle ki aithe mu naught I by 2R, semicircle 1 by 2, arc ki into alpha by 2 pi, where alpha is in radians, please. Okay, for example alpha 60 degrees icharu ikkada, then how you will write 60 pi by 3, 180 by 3, 60. Okay, suppose 90 degrees is given, what happens? Pi by 2, pi ante 180 kada, 180 by 2 90. Okay, alage 45 pi by 4. Okay, 180 by 4, 45 degrees. So alaga you can write in any fashion, 273 pi by 2. Like that you have to convert. This one put it in radians, please, not in degrees. Okay. So this is the formula for arc of a circle. Suppose when it is making arc, current carrying, magnetic field again inside, the magnetic field at here, this point C is given by mu naught I by 2R as it is into alpha by 2 pi. Pi value may the 22 by 7 or 3.14. Alpha angle whatever given is put in radians, please, and that will be the value. Clear? So mu naught I by 2R into alpha by 2 pi, please. Clear? Right. Any doubt? Let us go to the next one. Ala quadrant kuda ante kada. Quadrant also can do like the same thing. Quadrant enta avutundi? Quadrant also you can take. This, what is the total angle here? 90 degrees. Same ade formula avutundi. Again, going inside magnetic field, you can see. Magnetic field is inside again. Okay. So at this point, this is again radius R. So again it is making arc. Same formula. Mu naught I by 2R into alpha by 2 pi. Mu naught I by 2R, alpha by 2 pi. Here angle ante, angle alpha 90 degrees. So 90 and enta alpha. Just now I told you pi by 4, pi by 2, pi by 2. So put that value, you'll get the B value there. Okay. So to get the B value here, so what is alpha here? 90 degrees, 90 and then the pi by 2. So put it here, you'll get the value. That is mu naught I by 2R into alpha in radians, pi by 2 into 2 pi. Pi cancel, that is into 1 by 4. So like that you can calculate any structure if they give in the examination. Clear? Semicircle, circle, arc, quadrant, or general formula mu naught I by 2R vesi. Remaining all you can play with the subject. Clear? Now let us go to the next one. Suppose if they give circular coil at some point distance P or 1. Okay, this is the point, center point. This is current carrying coil. Suppose at a point P, already these things were discussed in gravitation and also in electrostatics also. Okay. So this point, for example, say some x. So here if you want B, dB or B. In such a case, radius R or A, anything you can take. So this formula is very easy. Suppose if n turns are there, if n turns are there, mu naught Ni R square by 2 into R square plus x square power 3 by 2. Okay? If n turns are there, if number of turns are there n, then this formula. If only one turn is there, remove that n. B is equal to mu naught I R square by 2 into R square plus x square power 3 by 2 at this point. The same fashion, the center C. At center C, what is x? 0. So put x is equal to 0. What is B value? Magnetic field mu naught I R square by 2 into R square plus x place lo put 0. Okay? Power 3 by 2. So R square power 3 by 2 enta avutundi ikkada mu naught I R square by 2 into R square power 3 by 2. 2 gets cancelled. R cube. R cube, and here what happens? 1 R is left over. Finally, you will get mu naught I by 2 R. Same thing circle. ఇందాక మన సర్కిల్కి ఎంత వచ్చింది? At the center, current carrying coil, mu naught I by 2R. Semicircle, 1 by 2. Quadrant, 1 by 4. Same formula. Clear? So same thing at circle, same formula. At the point P, general. For n turns, mu naught Ni R square by 2 into R square plus x square. Suppose if any case x is going to infinity, very large, then B becomes 0. Suppose if x is at infinity, then B is almost 0. Almost the value becomes 0. Then ekkada undi infinity ki vellipoyindi distance. So B value baga taggipothundi, it becomes 0, please. Okay? So this is how you have to understand. Okay? So at center C, when x is equal to 0 kada, 0 పెట్టేస్తే మనకి సర్కిల్ అయిపోయింది. సో అప్పుడు వాల్యూ మనకి mu naught I by 2R. Suppose if x is equal to infinity, again B becomes 0, please. Clear? Right. Now we will try to draw a small graph for this one. Magnetic field and distance x. In examination they are asking. We will try to draw a graph for B versus x. Okay? For this one. For example, this is the axis, x-axis, y-axis. This is the other side of x-axis, x dash. Okay? So graph enti magnetic field on y-axis, x distance on x-axis. So జాగ్రత్త చూస్తే maximum ఎప్పుడు వచ్చింది మనకి? When the maximum you got at x is equal to 0. This is x is equal to 0. At x is equal to infinity, again you are getting less value, B. So at x is equal to 0, you are getting maximum value. Okay? So the value graph ఎలా ఉంటుంది మీకు ఈ విధంగా ఉంటుంది almost on both sides. Okay? So at center this one. Value ఎంత వచ్చింది? Center point. mu naught I by 2R. Okay? This is B value ekkada at the center. Just like circular coil with one turn. Mu naught I by 2R. General formula mu naught Ni R square by 2 into x square plus R square power 3 by 2. This is the graph for B, magnetic field versus x. At x is equal to 0, center there ఏమైంది? Maximum value. And again x is equal to infinity, again B becomes 0. Infinity వెళ్ళినప్పుడు B తగ్గిపోతుంది. So the graph becomes like this. Maximum, again it is decreasing. Okay? Maximum decreasing. On negative side and positive side. Clear? So this is how you have to explain with the graph also. Magnetic field. For the circular coil carrying current I. Okay, clear? Now let us go further. This chapter maximum concepts are there also. Problems are also present. Now let us shift to Ampere's circuital law. Very, very important. Ampere circuital law, okay, or Ampere's law of conductor. Now what he say, the scientist is, for example, if we take any body, regular body or irregular body, see, this is irregular body, okay. Now in this, what happens is, if you take a small elemental length dl, and what happens if you draw tangent at any point, you will get the direction of magnetic field, okay. Now according to Ampere's law, what he says is line integral around the B dot dl is equal to mu naught times I inside current. Very, very important. Okay. So according to Ampere's law, because here you can take number of charges, some may be inside charges, some may be outside. Some currents may be going inside, some currents may be going outside. I told you before only, this symbol for currents, I1, I2, I3, I4, I5, I6. Some may be outside also currents, I7, I8. So according to Ampere's law, circuit lo em cheptunnaru, line integration around the closed circuit B dot dl is equal to mu naught times I inside. Mu naught times I inside. Very, very important, please. Very, very important. So by using this Ampere circuit law, we will try to solve for a long wire. Long wire ki em cheppagalra, already మనం solve చేసాం long wire ki. చూడండి, long wire అంటే infinity wire. Long wire is nothing but what? Infinity wire, minus infinity long wire. So here you can see this is the current carrying. So when current is carrying, what happens? Magnetic field inside, okay, it goes inside. So ఎలా వస్తుంది మనకి, ఈ విధంగా వస్తుంది circle. You can see here magnetic field is inside, it is going inside here and here outside. Here magnetic field is outside, you can see, here inside. అంటే ఎలా వస్తుంది, ఇలా వెళ్ళి coming outside, see like this. Okay, like this. Magnetic field going inside and coming outside like this. So here outside, here inside. So at that point, suppose if you take a small elemental length dl, and we all know if you draw a tangent there, you will get magnetic field direction. So here if you observe, B, dl, both are in same direction. Both are in same direction. Therefore, if you apply line integral B dot dl is equal to mu naught times I integral B, both B and dl are in same direction. Then what happens? Angle is 0, dot product. Mod B mod dl cos 0 is equal to mu naught times I, or integration B dl cos 0 1, that is mu naught I. Because it is circular, B is uniform. So B is constant, take outside, integral dl is equal to mu naught times I. Integral dl anta L. So B into L is equal to mu naught I, or B is equal to mu naught I by L. What is L? Length of the circle, that is perimeter. So since L is equal to perimeter 2 pi r, therefore B is equal to mu naught I by 2 pi r. So here I will multiply and divide with 2 to get the standard form. అప్పుడు ఏమవుతుంది, mu naught by 4 pi r into 2i. That's what we got in the before case ఇందాక వచ్చింది కదా, infinity long way. Mu naught by 4 pi into I by d. Mu naught by 4 pi and I by d into 2 times infinity way. Same thing again we have proved with Ampere circuit law. Whatever you have done before, same thing we have proved with Ampere circuit law. Mu naught by 4 pi into, ఇక్కడ r రాసాం, నేను సర్కిల్ కాదు, r is nothing but what, d. So mu naught by 4 pi into I by d into 2 times. అదే సెమీ ఫైనైట్ అయితే, సెమీ ఇన్ఫినైట్ దాంట్లో హాఫ్. అగైన్ సర్కిల్ mu naught I by 2r, సెమీ సర్కిల్ 1 by 2, క్వాడ్రంట్ alpha by 2 phi formula. So like that you can solve the problems by using this Ampere's circuit law. Okay, clear? So very important law solve this. In moving charges and magnetism, very important topics and ఇవన్నీ బాగా థరోగా రావాలి to get it into standard form. Okay? Now let us go for the next one. Magnetic field due to hollow cylinder. This is not a practical one, it is an imaginary, please. It is an imaginary cylinder. Imaginary cylinder. This is hollow because generally we don't have hollow cylinder. Hollow wires ekkada undavu. Wire and it is solid wire. But in some case they are asking this one. That's why it is an imaginary wire. Because if you take any wire, it will be completely solid. So here I am taking an imaginary cylinder and a hollow cylinder. Okay? So this is of course infinity. This is infinity, just like a wire. That side and this side. Okay? Suppose if you take such a cylinder, hollow cylinder is carrying current. Suppose imagine like that. Okay? Then what happens? Inside nothing is there, completely dull on the lopal and the hollow. Only on the surface the matter will be there, material. So in such cases we will try to find out B value. So magnetic field induction. Suppose magnetic field induction you want outside first of all. Let us calculate outside. Let the radius be capital R. Hollow cylinder imaginary. Okay. Now we will try to calculate somewhere over here point P outside. So here what? That radius R is greater than capital R outside. So when you are calculating outside, what happens? I told you number of times you have to take as the axis. Current at the axis, center point. Okay? Current at the center point. Therefore, B is given by mu naught by 4 pi into I by D. I by D అంటే ఇక్కడ ఏంటి? ఆ radius. I by D infinity wire కదా into 2 times. I by D ఇక్కడ ఏంది R తీసుకున్నాం కదా D బదులు. See here I am taking D is equal to R. This R is here. So I by R into 2 times. Okay, this is the magnetic field outside for imaginary cylinder. So B mu naught by 4 pi into I by D or I by R into 2 times. Adayinda? So observe carefully, this is outside. Okay? Clear? Right. Now coming to inside. So inside already we know there is completely hollow. So no current will be there. So what is B? Okay? What is B? Inside R is less than R, of course. Inside ante ikkada teesukundam point. And R is less than R. And inside even if you put this formula, mu naught by 4 pi into I by R into 2, current is 0. No current is there. Okay? So B is equal to 0. Since I is equal to 0, B is equal to 0 inside because it is imaginary cylinder. Hollow cylinder undadu ekkada kodani. Just for explaining you are taking. So B is equal to, because no current inside hollow. Only current is on the surface side. Clear? And finally on the surface, third one. Surface. Okay? B on surface. Surface means R is equal to capital R. And surface outside rendu same values ikkada. So surface emavuthundi again mu naught by 4 pi I by D into T, and here small r becomes capital R, surface kabatti. Here small r becomes capital R. Are you understand the point here? So inside 0, outside and on the surface same value you are having. Okay? Outside and surface you are having same value, please check it once again. Okay? And make a note, this is an imaginary hollow cylinder. Now we will draw a graph for this one. Inside you got 0, surface and outside you got the same value, please. Surface and outside you are getting the same value. Clear? Now I will try to draw a graph for this one. For this imaginary cylinder, we will try to draw a graph. So a graph draw chedam. This is x-axis. And what is the graph here? B versus magnetic field on y-axis and radius on x-axis. So this is the origin center. We'll try to draw a small hollow cylinder. Okay. So as you just now you have seen, this is at the center. At the inside. Inside and x is equal to 0. When x is equal to 0, what happens? B is equal to 0. Inside 0. Alage? This 0 ఎంతవరకు ఉంటుంది? Because ఇక్కడంతా complete hollow కాబట్టి this is completely 0. ఎంతవరకు? Up to here. And gradually it is increasing, you can see. Okay? 0. Already I have taught it in your gravitation chapter lo discuss చేసిన దాని గురించి. Gradually increasing. Okay? X is equal to 0 కదా చూడండి. Inside 0. Surface outside same value ఉంది. So again after that what happens? Again it is decreasing. You can see magnetic field is inversely proportional to R. Okay? So first it is 0 raised, again inversely proportional. Clear? This is outside. Outside. Outside and this one same formula we are having, you can see B inversely proportional to R. B inversely proportional to R. Magnetic field inversely proportional to the radius. So this is the graph for the hollow cylinder. First 0 up to the surface. Again slightly it is raised and again decreasing the value. Clear? So this is an imaginary cylinder and now let us go to solid cylinder. Practical one. Let us go to solid cylinder, practical one. Okay? Imagine ekkada undadu wire, because wire anta current pass avutuntundi. Okay, madhyalo gap gaani undadu. Now let us go to the practical cylinder, that is solid cylinder. Practical or solid cylinder. So this is the actual one. Solids and completely the matter is there. Okay. Of course this is also just like a long wire. Okay. Long wire plus infinity. Minus is just I zoomed the wire and I am showing you. This is the center one. Radius capital R. Okay. So here also for the solid cylinder, practical cylinder, once again we will start with outside. Outside somewhere point P here. Outside. So outside means here R. Okay. Small r is greater than radius capital R. Okay. So as usual outside, what is B? Infinity long wire kada. Consider the entire part at the center point B. So B is equal to mu naught by 4 pi. Same formula, I by D into 2. I by D into 2. I by D. D and nothing but your this thing. I am writing D is equal to nothing but your radius R. Outside point. Okay. So by R into 2. Because why it is infinity long wire? Infinity long wire. Therefore mu naught by 4 pi into I by R into 2. This is for outside place. So if you observe careful, outside B is what here? B is inversely proportional to R again. Magnetic field inversely proportional to R. Okay, outside. Now let us go to the second one. Solid cylinder. Surface. Okay. Surface. On the surface. On the surface means R is equal to capital R. Okay. Therefore magnetic field is equal to again mu naught by 4 pi into I by D. I by D and surface. D and R. I by D into again long wire kada into 2. Same formula. Only thing is R is changing here, surface. This is the second one. So here also you can observe magnetic field again inversely proportional to capital R. Coming to the last one, B inside magnetic field inside the solid cylinder. Inside the solid cylinder. So somewhere our point P ikkada తీసుకుందాం. Okay, inside. That means here what happens? Inside R is less than capital R. this whatever radius is, okay, less than this capital R. So for inside case, for solid cylinder, you have to remember the formula mu naught by 4 pi, okay, I by R square into small r into 2, okay. This is the formula for inside for practical cylinder. Mu naught by 4 pi I by capital R square into 2r. I by capital R square, I by capital into 2r. So if you observe carefully here, what is happening to inside? Inside, magnetic field is directly proportional to R. Inside, directly. Whereas outside and surface, you are having again same formula. Okay? You are having same formula, please. And అర్థం ఏంటి ఇక్కడ? You can observe carefully. Inside, as you go inside to the point B, you can see directly proportional to R. And అర్థం ఏంటి ఇక్కడ? Directly you can draw graph here itself. See. Directly you can draw graph here itself. So if you draw graph here for this one, watch carefully. X-axis 0, 0, that is magnetic field. On y-axis versus x radius on x-axis, we observe inside enti B directly proportional. Is x is equal to 0. X is equal to 0 ni chusinattagaithe, you can see this is the radius point. So it is directly proportional. Ekkada up to this one. Inside B directly proportional R. Then what happens again outside and surface same value decreasing. Outside. Clear? So again B is inversely proportional to R. So this is the graph again for the solid cylinder on x-axis and y-axis. B versus R. X is equal to 0 is surface varaku, inside ఏమైంది directly proportional, increasing. And then what happening inversely proportional outside. Surface outside same గా ఉంది. Clear? So this is how you can explain with the graph also, please. Try to understand the subject. Very, very important in the examination point of view. Clear? This subject is a very easy one if you understand, otherwise it becomes difficult for you. If you understand, it is very easy, graphs and other things. Only thing is, you have to concentrate on the subject while telling. Now let us go for solenoid. Okay? Magnetic field for solenoid. Now what is a solenoid? See, solenoid ante em ledante oka cylinder like structure untundi. Okay? It is a cylinder like structure. On this, wire will be wounded. Copper wire. Okay, and this will be the radius. Smaller or capital, and this is the axis. Okay, and the current will be going like this, in this fashion. I. Okay, this is the current. This is general structure of the solenoid. Okay, a wire will be wounding copper wire on the cylinder like structure. Okay, and here in this case the magnetic field induction given by mu naught into Ni. Very, very important. Mu naught is the same value 4.10 per minus 7 constant Henry per minute. N is number of turns per unit length. Ikkada N ante entante N by L. Number of turns per unit length. For example, L is the length of the solenoid. So divide by length, you will get a number of turns, small n. Small n is equal to capital N by small l. Number of turns per unit length. Okay, this is the, and I is the current flowing through the solenoid, please. Clear? And R is the radius. B is equal to mu naught Ni and small n is equal to number of turns per unit length. Okay, clear? Any doubts? Sometimes in the examination, they may ask for long solenoid. Long solenoid ante enti ikkada very long ante what is meant by long solenoid? Long means very lengthy, ante radius is very less, ante length is very much larger than R. And R is very much less than L. That solenoid is called as a long solenoid. Sometimes they are asking in NEET examination. Long and length is very much larger and radius is very much less. Okay. So in such cases, meeku B inside for long solenoid. B inside is given by mu naught Ni by L. Same. Okay. Where N is equal to number of turns per unit length, I is current passing, mu naught is equal to constant. ఏదైతే ఫార్ములా ముందు వేసారు సోలినాయిడ్కి సేమ్ థింగ్ ఏంటిది mu naught Ni by L. Okay. And you have to observe carefully here at the edges. At the edges, little less values there. Edges ఎంత ఉంటుందంటే half of the value. Half of mu naught Ni at the edges. Okay. The value little decreasing at the edges here and here. Okay. The center is maximum. దాంట్లో సగం అయిపోతుంది. Half of mu naught I at the edges, please. And if you draw a graph for this one, you will get in this fashion. If you draw a graph for this one, for this solenoid, x-axis, okay, long solenoid, total length L kada, so ఇది L by 2, okay. Now this is center point, origin, distance x here. So ఇక్కడ x versus మనకి b అనమాట. This is y, b magnetic field, and this is x. Okay. So if you observe carefully, edges దగ్గర ఏమైంది హాఫ్ అయింది, సెంటర్ దగ్గర మ్యాక్సిమం ఉంది. అంటే మీకు ఎలా ఉంటుందంటే రఫ్గా, okay, roughly it will be in this fashion. The graph for the solenoid will be in this. Okay. So at the edges you see the value is decreasing at the edges. Edges ఎంత అయింది mu naught Ni by 2, 2i. Mu naught Ni by 2. Mu naught Ni by 2. And here you are getting maximum value. Mu naught Ni, center. Mu naught Ni. So like this you can explain the graph also. At the edges it is decreasing 1 by 2 into mu naught Ni. At the center the value is maximum, mu naught Ni. Okay. Edges the value is decreasing, please. It becoming half. This is negative, this is positive wave. This is negative and this is positive. And this is the graph for magnetic field versus x distance. Okay. Distance x. X ante ade length. Okay. Clear? Right. Now let us go to the next part of the story in this one. Toroid. Another important one. Toroid. See, toroid is very simple one and toroid is nothing but solenoid, but when you bend the solenoid into a circular form, ring, it becomes a toroid. Toroid and name ledandi. Toroid is also called as toroidal solenoid. Toroidal solenoid ante ఇదే cylinder structure ni if you bend like this into circular form, then it becomes a toroid, like this, into a ring. Same solenoid, whatever the cylinder like structure is there, okay, coil is there, current carrying. If you bend this one into a circle, it becomes a toroid. So this is the basic structure of a toroid. Okay na? So this is how the toroid will be. Slightly different from the solenoid. Okay? slightly different from the solenoid. So current will be going and coming outside. Okay, current will be going and coming. And ikkada rendu untayi properties. Current going, coming like this. Okay, coming, going, coming. Okay. So like this will be there. So as you know, current is going inside, coming outside, inside, coming outside. Because symbols inside means this one, outside means this one. So here the radius, if you observe carefully, this is center point. This radius is A and this outer radius is B. So here if you observe carefully at the center, nothing is there. A toroid. At the center, you can see nothing current is there. So B is 0 at the center. So B will be 0 at the center. B at the center is 0 if you observe carefully. Okay? And you can see even if you take at the outside point also, okay, even if you take at outside point also radius, inside current emi ledu. Okay, completely it is vacant here. So B is 0. And formula goes same andi. Magnetic field B, same formula as solenoid, mu naught Ni. The only difference for toroid is, see here carefully, B is given by mu naught. Here N means what I told you, number of turns divided by length. So here in the place of small n, capital N by L into I. Here N is equal to number of turns per unit length, this L. So what is length here? Nothing but this cylinder is stretched into, formed into circle. So pi r, 2 pi r. So length and 2 pi r. Therefore, for toroid, B is given by mu naught Ni by length and 2 pi r average. Why I am telling average here? Because you are having radius, two radius, A and B, outer one. Inner A, outer is B. So A plus B, this R is nothing but what? Here R I can write as R average is nothing but A plus B by 2. R is average here, A plus B by 2, average value. Okay? Clear? So inside value, formula same thing and mu naught Nia, but only thing is N is nothing but capital N by L, where L is the perimeter 2 pi r, and R here is average and A plus B by 2. Two radius are there. And inside there is no current, so B is 0. And of course, even if you go outside value also, the values happens to be 0 only. Okay? So this formula is very, very important. R average you have to take in the case of toroidal solenoid because of two radius, small a and capital B. That's the point. Okay? Inside no current, outside also no. Clear? And we will do one numerical also to understand better manner. We will try to do one small numerical to understand a better manner. Let us do a small numerical. Okay? Are you following here? Right. Now I will give a small problem to understand better for this toroid or toroidal solenoid. అదేంటంటే నోట్ చేయండి. ఫర్ ఎగ్జాంపుల్ let us take N1. There are two toroids it seems. There are two toroids with the number of turns N1, N2, and they saying that current is same current in the two toroids. అంటే కాన్స్టెంట్ అని కాదు అక్కడ, సేమ్ కరెంట్. I1 is equal to I2 is equal to I. I1 is equal to I2 is equal to I. రెండు టొరాయిడ్స్ ఉన్నాయి ఇలాంటివి. ఫస్ట్ దాని నెంబర్ ఆఫ్ టర్న్స్ ఇచ్చారండి. He is given as around, I think, how much? 300. Yes. First one is given as 300 number of turns. Second one is given as 150 turns. 150, yeah? 150 turns. 150. Same current is there. Let us apply the formula. And the radius are given, average radius. R1 is given as around how much? 30 centimeters. 31. One is 30 centimeters, another is one is 50 and another is 30 centimeters. One is 50 centimeters, another is 30 centimeters. So directly you can put the formula. What is first one? B1 mu naught n. Original formula ఏంటండి? Mu naught ni కదా, original formula. So this n means what? Capital N by 2 pi r. 2 pi r and r average. I. Here I is constant, mu is constant, okay, 2 pi is constant. So what is left over now? B1 is equal to, I can put N1 by R average. This is equation 1. So I will apply the formula here. B1 is equal to N1 and the 300 turns. By first R average and the 50 cm. What is B2? Again N2 by R average. N2 and the 150 by, what is R2? 30 cm. Now let us divide B1 by B2. I'll write it here. B1 by B2 is equal to 300 by 50 cm. డివైడ్ చేసినప్పుడు ఇక్కడ ఈ 30 cm పైకి వెళ్ళిపోతుంది, కింద 150 ఉంటుంది. 150 once 2 times. cm cancel, 0 0 cancel. 3 to the 6 by 5. So I got it as 6:5. So when two toroids are given, same current is flowing in that one with different radius average 50 cm and 30 cm. If number of turns in the first one is 300, second one 150, the ratio of the magnetic fields are given by 6:5. So like this you can solve by using the formula for the toroid. Clear? So this is about solenoid and toroid, please. So in examination regularly they are coming. Please watch carefully and try to understand the subject and attempt in the examination, please. Okay. Next we will go to the force on a moving charge in a magnetic field. Okay. Force on a moving charge. Okay na? Force on a moving charge. Okay. Which force? Magnetic force, please. Magnetic force on a moving charge, positive charge plus Q. So this one, F is equal to magnetic force given by QVB sin theta. That is nothing but, you can also write as Q V cross B. Both are vectors here. Okay? V cross B. That means the velocity and magnetic field are perpendicular to each other. Okay? V is perpendicular to magnetic field. So cross product of these two gets the magnetic force. Q is charge, please. This is the force acting on a moving charge. Entadi? F is equal to magnetic force Q V cross B. When you do cross product, you will get QVB into sin theta. Again, you can get the direction by using right hand curl rule. And you have to observe when this force is maximum and when it is minimum. As you know, if you put theta is equal to 0, and the angle between V and B, suppose if theta is equal to 0, sin 0, 0 kabatti, magnetic force is equal to 0. In the same way, if theta is equal to 180 degrees, and V and B in opposite direction, then also sin 180 and the sin 90 plus theta cos, again 0. Again 0. Okay? So when theta is equal to 0, same direction, opposite direction, the magnetic force is 0. And maximum epudu 90 degrees. Sin 90 1 kabatti, maximum is, when you put theta is equal to 90, sin 90 is 1, therefore the maximum magnetic force is equal to QVB, newtons. Okay? So it is maximum for 90, minimum for theta is equal to 0 and 180. Next, Fleming's left hand rule. Fleming's left hand rule. So generally we are not using this left hand rule, but still, because it is there in syllabus, I am telling. Fleming's left hand rule and right hand rule. Fleming's left hand rule and right hand rule. But I won't use this one, but just I'll tell. See, Fleming's left hand rule means stretch your left hand in such a way that middle finger, forefinger and thumb finger perpendicular to each other. See, like this. This is forefinger, middle finger, and this is thumb finger. Three of them are perpendicular. Then what it tells is, forefinger indicates the magnetic field direction, middle finger indicates the positive direction motion. Motion, and it's also called as velocity. Positive motion, positive charge motion. Okay, and this indicates the magnetic force. Thumb finger indicates the magnetic force. Same thing for right hand rule. Right hand rule and stretch your right hand. Stretch your right hand like this. Stretch your right hand in such a way that three of them are perpendicular to each other, like this. Forefinger, middle finger, thumb finger. When you stretch like that, same thing, only the direction of magnetic field changes here. Direction of magnetic field changes, like this. See. Thumb finger, forefinger, middle finger. Same direction of current and motion of the positive charge. This is magnetic field direction. Again, magnetic force. Okay. So these are the rules given by Fleming's left hand and right hand. But I won't use left hand rule and right hand rule. But I will be using right hand palm rule and curl rule only for throughout the chapter. Because those are little easier to understand. Because when you use left hand, in some cases you cannot find out the force properly. But whereas in the case of right hand palm rule or curl rule, you can find out easily the magnetic force. So please understand, try to understand this one. Okay, in left hand rule, the middle finger, current direction, positive charge motion, direction of magnetic field and direction of magnetic force. Same way here also, right hand stretch it, three fingers, middle, forefinger and thumb finger. Forefinger indicates the direction of magnetic field, magnetic force, positive charge motion or direction. Now I will tell you the palm rule also to understand. Right hand palm rule. Okay. So this will be using in our future in next coming things. See, right hand palm rule. Right hand palm rule. Now what is right hand palm rules here? This is your right hand. Okay. This is your thumb finger. Okay, this is thumb. This is thumb finger and these are your four fingers. Okay, these are fingers. Now what he says is, for example, suppose this is the direction of say field, magnetic field. Suppose say this is the direction of magnetic field. Suppose some positive charge is there here. Okay. Now he is saying that this right hand palm rule, for example, what he is saying is, these four fingers put in the direction of the magnetic field. Okay? And this thumb along the direction of the motion of, for example, charge, positive charge. Suppose positive charge is moving this direction. So stretch your four fingers like this. These fingers along the direction of field and thumb along the direction of the motion. Then what happens? This palm is going inside. So the force is inside. Magnetic force is inside. This is how you have to utilize the palm rule. So palm rule em chepthanante, this indicates the direction of magnetic field. Thumb indicates the direction of the positive charge. And palm indicates the magnetic force direction. This is the right hand palm rule, please. Right hand palm rule enti, these fingers indicate the direction of the magnetic field in whichever direction. Thumb indicates the direction of the positive charge motion. And palm indicates, not this one, this one. Palm indicates the direction of force, magnetic force. And we will be utilizing this one in further chapter very easily instead of the left hand rule or right hand rule. Clear? Right. Now let us go still further. Hardly are we left over with the subject now. I think we are left over with only around another half an hour I think it takes. Subject is there. We will do one thing then. After giving 2 examples, I will stop this one. And again I will go in part 2, I will try to explain the remaining part. Because moving charges and magnetism is also not small one. It is bigger one. Let us not go a little faster. I will give some small examples and end up this one as a part 1, moving charges. And in part 2, remaining part, I will complete it. With a half an hour is there again. Okay. So let us give some examples to understand the palm rule. See here. Examples for palm rule, right hand palm rule. Palm rule. Okay. So right hand palm rule lo one example chadam to understand better. To understand it better. Okay. So here what a magnetic field is inside. Now here I am taking a positive charge. Here a positive charge is there. And of course this is the direction. Now in this case how to find out by using palm rule? See, just now I told you, put the palm. Direction into magnetic field inside. So put like this, inside. Put these 4 fingers inside. Now what is the direction of magnetic charge, positive charge? This is the direction. So this is the palm indicating an upward direction. So magnetic force is in upward direction. First case. Stretch your fingers. Put these fingers along the direction of the magnetic field. And what is the direction of the positive charge? This is the direction. So this palm is indicating upward direction. So force will be in upward. Same thing we'll go for the next one. For example, this is the direction. Magnetic field. Now same positive charge. Suppose now it is in this direction. Now how to find the magnetic force? See again same. Put the fingers along the direction of magnetic field. This is the direction of positive charge and palm is indicating downwards. So here now the magnetic force is downward direction. Now let us go to the another one. Yes. ఈసారి కొంచెం డిఫరెంట్గా వెళ్దాం. Field is outside. Magnetic field is outside. Okay. I'll take some positive charge in this direction. Now for this, how we will calculate the magnetic force? See, field is in towards you. Field మీ వైపు వస్తుంది, కెమెరా వైపు చూడండి. See, field is towards you. And you can see velocity, direction of the current in this direction. So, field is in this direction, this. So, what is the palm showing? Downward direction. So, magnetic force will be downward direction. So, field is coming towards you. Field is coming towards you. And what is this thumb indicating the direction of motion? Palm coming down. So, this is the magnetic force. Suppose in the examination if you give negative charge, suppose ఈ positive బదులు negative ఉందనుకోండి, same process but change the force direction. Instead of positive he is giving a negative, for example ఇది తీసుకోండి. Okay, put like this, upward direction. Because it is negative charge, in this case the force will be downward direction. The same way here, if suppose negative charge is given, okay, put like this direction, this is direction of the motion of the charge, positive charge, and this is the value got. But because it's a negative charge, put it in opposite direction. In the same way here also, you can see, okay, magnetic field direction, and this is the motion of the charge, positive charge, and this is the force. So because it's negative charge, change it into the opposite direction. Instead of positive, they give negative, change the direction to the opposite side. So this is how the palm rule is used in the examination, and thereby the solution is done. What I will do is, Remaining half an hour part is left over, a few part. Okay, that is Lorentz force and work done. Okay, and also electron when it is revolving, what is the radius? Okay, cyclotron, and force between two parallel conductors carrying current, same direction, opposite direction. Okay, so all those I have left over, and again torque, moving coil, galvanometer formula, that I will be dealing in part 2 of moving charges. Half an hour part is left over. Already I have taken almost 1.5 hour or 1 hour 45 minutes class now. So next part in moving charges, I will be dealing about those. Okay, so prepare well please. Right.